Hello everyone, my name is Akhil and today I'm going to discuss about the gyroscope sensor. So we'll see the contents of the slide. First we'll see the introduction of gyroscope. What is it? How is it useful? Then we'll see the types of gyroscope sensors and their working principles. Third, we'll see the error observed in calculating the angular velocity or the output of the gyroscope sensor. Fourth, we'll see the applications of a gyroscope sensor. So starting in the introduction, what is a gyroscope? So a gyroscope is a device used for measuring or maintaining the orientation and angular velocity of a particular device or an object. Generally, these sensors are based on principle of angular momentum, conservation of angular momentum, but the working principle may vary depending on the type of sensor that we're using. So there are mainly three types of gyroscope sensors. The first one is ring laser gyroscope, second is fiber optic gyroscope. Third is micro electromechanical systems, which is known as MEMS. It is not specifically designed for a gyroscope, but it can be used for is you can use as a gyroscope sensor. So starting with the ring laser gyroscope. So this is the design. We can see two light sources coming out of different directions, which are in opposite direction. So we can determine that it is based on optical phenomena, and this optical phenomena is known as Sagnac effect. So what is a Sagnac effect? We'll discuss in the next slide. So when a light is sent in the opposite directions in a closed path on a rotating disk or any path, rotating object. So in this example, we can see that the disk is rotating in the clockwise direction. So the right side light will cover less distance as it is rotating in the clockwise direction. So the right side light will reach the detector first, whereas the left side will reach later at the detector. So we can say that the detector detects different frequencies as both of them reaches the detector different time at different times. So using the differences in these frequencies, we can determine the angular velocity of a object. Uh, in here we can see this is the basic design of an aerospace industry RLG. There isn't much difference between the both of them. In here, instead of using a direct laser source, uh, it has two anode terminals, and a cathode terminal, and they have mirrors for reflection of the laser light, and the detector is placed here. So and this cavity is filled with the helium neon gas. So when a voltage is applied over it, a laser will be generated in both of the directions, which is coherent. So no phase difference will be between these two laser sources. And when the device rotates, due to the Sagnac effect, the one in the right, if it is clockwise, the right will reach first, and the left one will reach later. So by calculating this difference in frequencies, we can determine the angular velocity. But there are issues in RLG which is known as lock-in effect. So lock-in effect is the inability of an RLG to detect a motion below a specific rotational limit. So let's say if it is rotating with 0.01 degree per second, this RLG can't detect these changes because the difference in frequency is less. So the output of the system will be zero. So to fix these issues, there are two methods. The first one is by using servo motors. So these mirrors are fitted with motors which will vibrate with a specific resonance frequency. So when the light falls on them, one will they are designed in a way that one will make them faster. So if we set it to the right side to be faster, so this light will be coming to the detector faster, whereas the left side will be reaching later. So even for a small movement in rotation, because of this huge uh, vibrations, they can still detect these changes. The second thing is to use a piezoelectric dithering motor. So dithering is a method of generating a error so that we can improve the sensitivity. So in here, in this case, we are using the error to be the rotation. So instead of making the RLG static, we will rotate the RLG in a clockwise or anti-clockwise direction with the specific RPM. So even for a small rotations due to external factors, these difference in frequency will still be observed and can calculate it. And to offset the errors because of this dithering motor, a calibration will be needed in the out detector system. And after the calibration, we can use the device without any error. Next, we'll discuss about the fiber optic gyroscope. It is similar to that of RLG. The basic principle of working principle is also based on Sagnac effect, but the design of the FOG will be different to the RLG. So this is an FOG detector or sensor, and this is the design. This round coils is the optical fiber. So when a light source is emitted or sent through both of these ends, due to the Sagnac effect, one will reach at the detector faster, one will reach at the detector slower, and which will result in change in phase difference. So by observing this interference pattern or the change in interference pattern, uh, we can determine the rotation or rotation rate or angular velocity. So we have seen that both RLG and FOG have basic principles that work on a Sagnac effect, but there are certain properties that they have differ in. So these are the differences between both of them. We can see that RLG is based on the frequency difference of the two inputs or two optical sources, light sources, whereas FOG is based on shift in fringe pattern or a phase difference. RLG have many disadvantages such as it has lock-in issue, it is heavier, it is expensive, it is also sensitive to environmental factors or environmental changes. Whereas FOG doesn't have much issues, it doesn't have lock-in issue, it is light and compact, it is cheap, it is insensitive to environmental changes. But RLG is superior than FOG in one such aspect, it is the error. RLG doesn't have very huge error. It's just 0.001 degree per hour, whereas it is zero point 0.1 degree per hour in FOG. Even though both the errors are small, for an accurate system, RLG is more preferred than FOG. But for many systems, FOG is generally useful as it's cheap and compact. And the third is gyroscope in MEMS. So MEMS is a board which contains different modules for different parameters. So here are different parameters such as accelerometer, magnetometer, and gyroscope. We'll discuss the gyroscope in the MEMS. So it is based on the effect called Coriolis effect. So when a body is in moving in a direction and and the rotation is introduced into the system, the force known as Coriolis force will be generated perpendicular to the movement and the axis of rotation. So in this case, we can see that the velocity is along x direction and the axis of rotation is along y direction. So perpendicular to both, force known as Coriolis is generated along z direction. And using this principle, this gyroscope will be working. So we'll see the working principle here. Uh, this is the basic design of a gyroscope in an MEMS. So it contains a mass element so that the body will vibrate. And these are the spring-like components, these green components. And this driving direction is the velocity in direction in which it is moving. When the only velocity is applied, these are the capacitors that are useful in getting the angular velocity. So these capacitors doesn't have a huge change in length, and even though there is a change in area, it isn't much and can be easily neglected. But when there is a rotation introduced due to the Coriolis effect and Coriolis effect, there will be a force acting along z direction. So these capacitors will move in left and right and can change the length. Because of this change in length, the output capacitance will be varying. And by detecting the change in capacitance, change in capacitance, we can determine angular velocity. We have discussed three main types of sensors used for gyroscope, and now we'll see the errors that can be observed in this sensor. So the first and foremost is the bias offset error. Even when the input rotation is a null or zero, the detector can still give an output. The sensor can still give an output which is non-zero. And this is because of the environmental factors or noise from the environment. So to fix this, we can easily fix this using calibration. And then the second is temperature sensitivity. So gyroscopes are very much sensitive to temperature, and the performance and sensitivity depend over a temperature. So it is important to make sure that temperature won't change, or the error because of the temperature will be zero. So there are three methods to fix the error because of temperature. One is temperature isolation. We'll make sure that the temperature of a gyroscope will be constant so that error is zero. The second is temperature compensation. We'll be using an external sensor to detect the changes in temperature, and by detecting the change in temperature, we can do some calculations or calibrate the device so that the error will be zero. And the third and mainly important fix is by using a scaling factor. So we'll consider that output of the gyroscope is linearly proportional to temperature, and we'll find the scaling factor by doing various experiments. And using this scaling factor, we can calibrate the instrument over different temperatures so that we'll get accurate results. And the third is shock and vibration sensitivity, or the error because of the vibrations of an external force or vibrations. So this can be easily be fixed by using a vibration isolation platform or enclosing it in a shocking proof casing. And the last and main important factor is bias instability. It can be due to many factors such as aging, stress on the device, mechanical stress, temperature, environmental conditions. It is hard to offset, and the performance of a gyroscope is mainly depend on the bias instability. So it is necessary to fix the error or make the error to be zero. So there isn't any easy method to make the error zero. Uh, but one such useful fix is to use multiple gyroscopes, and by using the outputs from these multiple devices, we can offset the error or the compensate the error because by the other devices. So we will discuss the applications of a gyroscope in now. Uh, so there are many applications of a gyroscope. Here are five such important applications. The first one is navigation. It is useful in determining or getting information about the angular velocity and orientation of a device, so that the navigation system can easily determine the position and accuracy with accuracy. The next is robotics. So it is also used in robotics to provide stability to the robots. It is also used in to control the orientations of robotic arms in industries, etc. And in aerospace, it is important component so that the pilot knows the orientation and to control its movement. And next is seismic monitoring. As we have seen, it is very much sensitive to vibrations. So it is useful in observing the seismic activity in the earth. So when there is a slight movement, these gyroscopes can easily detect this earthquakes or seismic activity and can predict the earthquakes. The last and important is in automotive industry. So right now, the Tesla is using a gyroscope or any electrical cars with autonomous driving system have a component called electronic stability control, and it is useful in getting the information about the vehicle's orientation and the movement so that it can prevent accidents or rollouts in the roads. So there are many applications of gyroscopes. These are the main applications, and the gyroscope is still improving. Right now, the main research is going on FOG to to improve the gyroscopes because they are cheap and much more compact, and RGL is generally used for more accurate results. So here are the references that I have used. Thank you.